All right, so we're going to look at, and we're now recording, we're looking at 1998 question 6. And this is a simulation question. And one of the reasons we wanted to do this is we did not get to spend the time on simulations we'd like to. Plus, there are a few other things that are pretty important about this problem, and we'll address them as we go through it. So the manager of a cultured pearl farm has received a special order for 2 pearls between 7 millimeters and 9 millimeters in diameter. From past experience, the manager knows that the pearls found in this oyster bed have diameters that are, oh, there's a wonderful key word, normally distributed with a mean of 8 millimeters and a standard deviation of 2. The manager wants to know how many oysters he should expect to open to find 2 pearls of the appropriate size for this special order. So we're looking for 7 to 9 millimeters, and we're going to need 2 pearls of that size. Complete the following parts to design a simulation to answer the manager's question. Before we do that, I want to go ahead and just real quickly sketch out what we're working with. We're working with a normal. We have a mean of 8, and we're looking for something between 7 and 9. This is what we're looking for. And then we also know that our standard deviation is 2. So the very first question was determine the probability of finding a pearl. Now is nice of them. That means A means singular, so just 1. Even though he wants 2, right now we're only concerned with 1 of the appropriate size and an oyster selected at random. Express this probability as a number between 0 and 1. Round the probability to the nearest 10th. Don't skip that part. Otherwise, the test becomes a little bit more challenging. So our probability is between 7 and 9, and that's what we showed graphically, that we're looking between 7 and 9. And we set up a z-score, and we're going to set up a z-score using, well, first off, let me write that down. The largest one first minus the smallest one. Now I can do this by doing a norm CDF, probably be the fastest. So doing the norm CDF, this is going to look something like this. Second vars, norm CDF, lower bound 7, upper bound of 9, mean of 8, and standard deviation of 2. And we end up getting a probability of 0.3829. Now they said they wanted us to round to the nearest 10th. Well, the nearest 10th in this case is going to be 0.4. Okay? All right, continuing on. Describe how you would use a table of random digits to carry out a simulation to determine the number of oysters needed to find 2 pearls of the appropriate size. Include a description of which what each of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 will represent in your simulation. Well, first off, this was really nice of them to have us round it to 0.4, because that means I can use 1-digit numbers. And basically, I need 40% of my numbers, and right here I have 10. And I just said, you know what? These are that's 4. I'm going to circle those 4, and those 4 are going to be the ones that I say are oysters with the appropriate size. Now, technically, as long as I choose 4, I could choose any 4, but usually it's best to choose with the grouping, and I usually like to start with 1. So I would assign 1, 2, 3, and 4 as oysters containing the pearls of the appropriate size. Must show the assignment. Then we need to address the other numbers. Well, I would assign 5 and 8 and 0 as oysters that did not have pearls of the appropriate size. How am I going to go run this thing? Well, I would work from left to right, and I would allow repeats. Let's address repeats real quickly. Anytime I'm working with percentages, we can go ahead and say that we're allowing repeats. Beyond that, you need to read the question to determine whether or not repeats will be allowed. All right. And I will do that until I had two numbers that represented oysters containing pearls of the appropriate size. And it's real important that I say I have two numbers because I need to have two pearls. Sometimes you only need one, sometimes you're going to need much more than two. But here I need two numbers because I need two pearls of the appropriate size. I would then count the number of single-digit numbers that had been inspected, because that would represent the number of the oysters necessary to have opened in order to obtain two pearls of the correct diameter. I would repeat the process numerous times and average the results from the trials. And at this point, I'm going to pause this because I know it's a fair amount of writing. Record. So then they ask us to say, perform your simulation 3 times. That is, run 3 trials of your simulation. Start at the upper leftmost digit in the first row of the table and move across. Make your procedure clear that someone can follow what you did. You must do this by marking directly on or above the table. So first off, I said that 1, 2, 3, and 4 represented oysters of the correct size. So if I'm looking at this, I'm going, hey, that's a good one. Not, and even though that's a repeat, that's a good one, and there's the end of my trial. Well, I had to open, and this is what that third part on part B said. How many oysters did I have to open? I had to open 1, 2, 3, 4 oysters. So I opened 4 oysters in order to get the 2 that had the right size. Then I went and go, okay, now technically I can start the next trial right at any point on here I could, but usually, and this is what I would recommend, that if you get to run a simulation, drop to the next row. It just makes it cleaner for you and cleaner for the grader. And believe me, you don't want to cause them any issues. So the next thing, I come up with a 7, that's the wrong size. 1 happens to be the right size, 9 is wrong, 5 is wrong, 0 is wrong, 2 is correct. So in this case, 1, 2, 3, 4, 5, 6 oysters. And then I do it again for the third one. 1 is the right one, wrong, 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 and correct. Thank you so much. I'm sorry about that. Here, I'll slide this off so you can take a look at what I actually have. So I ended up having 4 oysters. I marked the green ones as the correct size, and the yellow ones were the ones that were wrong. So in this case, I opened 1, 2, 3, 4. Here I opened up 6. Here I opened up 7. But in all 3 trials, I only had 2 successes. I only had 2 that had the correct size pearls. So then I make a table, and this is really key. Make a nice little table, and you label it trials. And here I had 1, 2, 3 trials. And then how many oysters? Well, 4, then 6, then 7. So I opened up a total of 17 oysters, and I divided it by 3 trials. All right. And so based on my simulation, or based on our simulation, we would expect to open an average, and these are keywords, of 5.67 oysters in order to find 2 pearls of the correct size. I'll pause at this moment. Okay, so part D, the same question. The results of 2 100 trial simulations. So they're going to show us 2 100 trial simulations. One researching for pearls between 7 millimeters and 9 millimeters, and the other between 4 and 6.5 are shown below. So we have distribution A and distribution B, and they ran those and they gave this to us. They gave us these graphs. Well, we've already calculated the probability 7, 9, so I just brought that over. We did that on the very first page as part A. So that was from part A. I wrote it down here for our purposes in this classroom. Once you've written it down once, you don't have to write it down again. But since I'm on a separate sheet of paper, I thought it would be helpful for this. So this would be 7 to 9. Then I did the same probability, did the same calculation, but then now they're talking about between 4 and 6.5. Well, I still have a mean of 8, but now they're looking for 4 and 6.5. Our standard deviation is still 2. And I'm looking for these values right here. And I just went ahead and did another norm CDF, second vars, norm CDF for 6.5, mean of 8, standard deviation of 2. And that's where I got that value, the 0.2039. So that's how that came about. Then they ask a fairly tough question. They said, identify which distribution A or B represents the search for 279 millimeter pearls and explain your reasoning. So I'm looking at this and I go, well, there's a 38% chance of getting one that's the right size. And here there's a 20% chance of getting one the right size. So clearly this would take longer to find and this would be shorter to find. I have a 40% chance of success or 39% chance. Here I have about half that. Well, when I look at these two graphs, and I can't fit them on the screen very easily, so you're gonna have to look at your papers, you can see that this one is further stretched out, which means it took more chances, where this one took fewer. So this means this one had a greater probability. And this was actually the type of answer they were looking for. Finding a pearl of 4 to 6.5 millimeters is less likely than finding a pearl of 7 to 9 millimeters. How do I know it's less? I said it was 20%. And for that reason, would on average take longer to find. Thus, distribution B is the simulation of the 4 to 6.5, and distribution A simulates finding a pearl 7 to 9 millimeters. All right, pause this for a second. So I'm going to continue with question D, although we've answered it, and we said A went with the 7 to 9 millimeters, and B went to the 4 and 6.5 millimeters. I'm going to look at this from an alternative perspective, why it gives me a chance to talk about the geometric distribution. So if we know that this probability was 38%, and we are going to continue until we have our first success. And since we're continuing until we find that pearl of the right size, continuing to the first, that makes it a geometric. Well, the geometric has an expected value of 1 over p. So 1 over 0.3829 equals 2.611. All right. So the probability of finding one pearl, the probability on average, I should say, we'd expect to find the first pearl of 7 to 9 millimeters after 2.6 oysters. But they didn't want just one, they wanted 2 of the right size. Well, remember, we can add means directly. So I can just add 2.6 plus 2.6. So for me to find 2 pearls of the right size, I would expect to have to open 5.22. All right. So, what do I expect to hear? Well, look at this. The expected value. We expect to, and you do need to pay attention to this because I will ask about this in a moment. 2 times 9 divided by 100, because there was a 100 trial simulation. So there's a 9%. 3 times 0.22, 4 times 0.2, 5 times 12, etc. This would be your work shown. Now, for on the calculator, I could have gone to stat edit, and I'm not going to take the time to input all of these, but I could have just put 2 into L1, followed by 9 into L2, and it would calculate it automatically for me. All right. And I could do a stat calc 1 var stats, and that would give it to me. And if you need to ask questions on that, I'll do that in a little bit. Alternative, we calculated this probability already. The expected value is 1 over 0.2039. So to find one pearl, on average, we'd expect to have to open 4.9. Well, this would be 9.808. Well, when I did all of these, the 2 times the 0.03, 3 times 0.06, and did them all the way out to find two pearls based on the simulation was 9.36. My theoretical was 9.808. This was the theoretical. Up here, this was my theoretical, and this was my simulation. So clearly, those two are close together, and these two are close together. So consequently, we could look at this and go, you know what? Through a geometric, I could do a geometric expected value and find that B went with a 4 to 6.5, and A went to 7 to 9. Now I'm going to pause to ask for questions on this. Okay, so part E says use the appropriate distribution to compute an estimate of the expected number of oysters to find two pearls between 7 and 9 millimeters. Well, in part D, we said distribution A was appropriate. All right, now if you'd chosen the wrong distribution, you can still get credit for part E, but Mrs. Lamb will address that in a moment. So how in the world am I going to take this chart and find the expected number based on the simulation they ran? Well, this is what I just did a moment ago. 2 times the 0.09, 3 times the 0.22, 4 times the 0.20, 5 times the 0.12, all the way to 14 times the 0.01. All right. And when we sum those up, based on the simulation they ran, we would expect it to take 5.16 trials. So this was not part of the problem, but I want to bring this up because it showed up on things that they very well could ask. And they said, calculating a p-value based on a simulation. All right. Well, p-value is the probability of getting a test statistic this extreme or more, given the null is true. So what is the probability for distribution A that it took more than 12 oysters to find two? What's the probability to take more than 12? And they gave you this graph. And so they go, okay, here's the simulation we ran. Based on your simulation, what's the p-value? Well, more than 12, if I want the probability that X is greater than or equal to 12, I'm gonna go, well, here's 12. So 2, 1, 1. So that equals 4 out of 100. So my p-value in this case would be 0.04. And if they asked me to, is this statistically significant? Well, I could put a p-value here, say an alpha of 0.05. And I go, hey, that's less than. So it's unlikely that I would have to open 12 or more oysters. Not very likely that I'd have to open more than 12 oysters. On the other hand, when we went to B, if they were still looking for this probability that X is greater than or 12 at that p-value, I added all these up and then added up to 27, which is 27 over 100. That's a pretty large p-value at 0.27, which is greater than any reasonable alpha. So we would fail to reject it and say that it's not, it's not that unlikely. It could happen quite frequently by random chance. Okay, so if they give you one of these graphs and said, what's the p-value? Well, what are they interested in? I wanted it greater than 22. Okay, well, in this case, 1 plus 2 is 1 is 4. Then it would be 4 out of 100. I wanted it more. What's the probability that it's more than 16? Just find that cutoff, add them up. And it could be going to the left-hand side. What's the probability that it takes 4 or less? Well, 4 or less would be 7 plus 6 plus 13. 7 plus 6 is 13, plus 3 is 16. So in that case, the probability that it would be 4 or less would be 16 out of 100 or 16%. Okay, so you can actually calculate p-values from these as well, from these simulations. You're good.
All right, looking at the grading rubric, this question is from 1998. Some of the things that they were looking for back then and things that they look for now is a little bit different. But they divided it up into 3 sections. So part A was section number 1. They were looking for you guys to show some sort of work. Back in 1998, showing work might have just been a calculator command. I don't suggest that that's something that would count for good work now. Mr. Spencer and I are always talking about doing formulas and doing curves. So I don't know that I would really listen to that bit because, like I said, this is very early on in the AP stats testing. So you need to show your work and come up with your probability. If you did that correctly, then for this section 1, you got essentially correct. The rubric, according to this rubric, said that if you came up with that answer without showing work, they would still give you approaches, which is kind of like equivalent to a P now. But again, that is not the trend these days. You must show work for all calculations, and so I would highly suggest that you always do. For section number 2 was parts B and C. There was quite a few things that had to be addressed when you're running the simulations. First, you had to do a well-defined simulation talking about what is a success, what fits the success criteria and what doesn't. It was easier to use 10 digits, but they did make a note that there was other options available. If you wanted to use 2 digits would also be acceptable as long as you were well-defined. So you need to describe the appropriate method, talk about getting your 2 successes, and running the trial 3 times. And if you ran it more than 3 times, that wasn't a problem if you accidentally kept going, but you used 3 to do your approximation. And again, like Mr. Spencer says, depending on your definition of what success is like, your numbers could be slightly different. He decided success was 1, 2, 3, 4, but if you chose 0, 1, 2, 3, your numbers might be slightly different and your work looks different, and that's totally fine. So if you did all of those things, then for section 2, you could get an E. And if you're missing parts of it, they looked at it kind of holistically as whether or not you had enough information presented to get a P or not. Then for section number 3, which is D and E, they are looking for work that is similar to what Mr. Spencer showed, or in his alternate solution was also listed as a possible solution. Let me look here. It was possible that you did not get the correct answer in D, but got a correct, based on doing good work in part E, that you could still get full credit for part E. So if you did part D and E correctly, that's an E, but if you missed D, but showed reasonable logical work on part E, you could still get a P for that part. So overall, to get your score for this problem, we needed to get 3 E's for a 4. To get a 3, you needed 2 E's and 1 P, or 1 E and 2 partials. And then for a 2, it's 1 E and 1 P. And then for a 1, it's 1 E or a 1 or 2 P.